Hello everyone, welcome to this session on strain energy concept, that strain energy principle and theorems. So continuing from the previous class, we had solved some problems related to strain energy method, and there are some application of strain energy method, and amongst those particular application of strain energy theorems and strain energy equation is the first equation or the first theorem, what we call it as the Castigliano's theorem. So Castigliano's theorem, there are two theorems related to Castigliano's. One theorem or the first theorem is related to find out the deflection, and the next theorem is to find out the slope of a particular at any point. To find out deflection, the Castigliano's theorem says is the strain energy, the partial differentiation of strain energy with respect to load will give the deflection at any point. Please do remember, the partial differentiation of strain energy with respect to load will get the deflection at that particular concentrated point. Likewise, the partial differentiation of strain energy with respect to moment. See earlier part, first partial differentiation of strain energy with respect to load we shall get deflection. Likewise, the partial differentiation of strain energy with respect to moment we shall get slope at that particular section. So what is strain energy? To recall that, strain energy expression what we had derived in the previous class for bending, it was m square dx divided by 2ei. So this will be, if I partially differentiate the same term, this term will come as 2m dou m by dou p, because partial differentiation of strain energy, E is constant, that is modulus of elasticity is constant, I is constant, so I will be differentiating this m term. Differentiation of m square will come as 2m dou m by dou p. So when I differentiate this strain energy with respect to load, I will be getting deflection at that particular cross section or that particular point. Likewise, the same strain energy, when I partially differentiate with respect to a moment, then I will be mentioning it as a slope. Now what is the hard and fast rule to call P to delta and M to slope? Always load will create a displacement or force will create a displacement, and moment will always create a curvature. Curvature means a rotation. For that reason, it is always essential to find out the slope at any point or cross section. It is essential to have a partial differentiation with respect to a moment. Interchanging the parameter will never yield any form of values. For that reason, it is very much essential. If I want to find out deflection, I need to partially differentiate strain energy with respect to load. Likewise, to find out slope, I need to partially differentiate strain energy with respect to a moment. When I find out this particular term, then I will be getting the slope at any position and deflection at any position. Most important thing is, wherever I want to find out the slope, wherever I need to find out slope, it is very much essential that I need to have a moment at that particular point. Moment means couple at that particular point, either in the clockwise direction or in the anti-clockwise direction. It is very much essential to have a moment or couple at the position where slope needs to be evaluated. In case if it is not present, then we need to introduce a dummy moment or a virtual or fictitious moment at that particular position. Then only we need to partially differentiate it. If we don't have a moment and then differentiate it, obviously the whole term will come out as 0. As a resultant, slope at that particular any section throughout the length of the section throughout the length of the beam will remain 0, which is practically not possible. For that reason, if we have a moment, well and good. If we don't have a moment, then we need to introduce a dummy moment or a fictitious moment at the position where slope needs to be calculated. Then partially differentiate with respect to a moment. The same condition prevails if I have a cantilever beam carrying a UDL here. Now, if I want to find out a deflection at the free end of the beam, so here it is essential that I need to have a concentrated force at that particular location. If I don't have a concentrated force at that particular location, I need to introduce a dummy or a fictitious force. This dummy or a fictitious force will ensure that the deflection will be evaluated at the position the deflection will be evaluated at that particular position where the frictious force has been imposed. If I impose the frictious force at the free end, which indicates the deflection is calculated at the free end. If I impose the same frictious force at the mid location, then the deflection will be calculated at the midpoint of that particular beam. In that particular condition itself, the deflection can be calculated. If you already have a point force, then there is no essential to put any dummy force in that particular situation. If it is already been present, we can straight away consider it in the equation and then partially differentiate it. If we don't have, then we need to impose a frictious force and then continue with the solution. To just have a small example. So this is an example. What it says is determine slope and deflection at the free end of a cantilever beam as shown in figure. So I shall consider a cantilever beam carrying a point load P at the free end, and this particular cantilever beam span I shall consider it as L. I need to find out a deflection at the free end of the cantilever beam. So free end of the cantilever beam, there are 2 points in the cantilever beam, A and B. Amongst these 2 points, A is been provided with a support and B doesn't have a support. So the support provided at A is fixed. So obviously, wherever there is a fixed support, deflection will be 0 and rotation will also be 0. Rotation to be 0 at A is because fixed support carries 3 reaction components: vertical reaction, horizontal reaction, and then the moment. Vertical reaction will ensure that the beam will not move in the vertically downward direction. Likewise, horizontal reaction will ensure that the beam will not be displaced along the horizontal direction or along the x direction. And movement that has been present at A will ensure that slope at that particular location will be 0. So for that reason, slope and deflection for the fixed end will be 0. On the other hand, at B we don't have a support. Since we don't have a support at B, we always have a deflection at B and also slope at B. Now this is what is the task in hand and the problem in hand, to find out deflection at B and slope at point B. To find out deflection at B by Castigliano's theorem, delta B will be, expression will be partial differentiation of strain energy with respect to load. So strain energy expression is U is equal to integration 2m square dx, m square dx divided by 2EI. That is what is the expression of the strain energy. U is equal to integration m square dx divided by 2EI. So if I want to find out deflection, I need to partially differentiate this particular strain energy with respect to load. If I partially differentiate this will be 2m dou m by dou p dx divided by 2EI to find out deflection. Likewise, to find out slope, I shall consider the same strain energy expression, but instead of P, I shall partially differentiate with respect to a moment. So the theta B will be equals to 2m dou m by dou m dx divided by 2a. So coming on to the solution of theta B, I shall take it at the later stage. First I shall find out the delta value at point B and later find out the theta value at point B. So if it is a beam, cantilever beam subjected to a point load at the top, so this particular beam will have a hogging pattern of bending, and this particular displacement at B will be called as delta B. Then if I draw a tangent at this particular tip of the beam and then evaluate by using any measuring device, and that particular angle shall be called as theta B. Now to find out delta B, I need to find out strain energy expression first. To find out strain energy expression, what is strain energy expression here? U is equal to integration m square dx divided by 2EI. What is m? M is a moment. So I shall find out first the moment term and then substitute in the delta term. So section shall start from B. When section starts from B, x value at B will be 0. Then it shall proceed towards A. As it proceeds towards A, and ultimately when it reaches towards the last destination point at A, x value will be L. So at any position, intermediate position, it will be mentioned as a variable x. So moment at x will be P into x. Direction of rotation clockwise with reference to A. P is on towards the right hand side, will rotate in clockwise direction. That's why it is positive P into x. keep this particular term as it is. Now after expression, here it is 2m by dou p. So if I differentiate this same term, dou m by dou p, please do remember it is not dou m by dou x, it is dou m by dou p. So here I shall partially differentiate with respect to p. So what I shall have here is p is to the power of 1. P is to the power of 1. So partial differentiation of p will lead to a coefficient as 1 into x. So which will be dou m by dou p as x. So substitute in the delta b term, delta b will be equals to integration 2m dou m by dou p dx divided by 2ei. So substitution of these terms will be 2, keep 2 and 2 in the numerator and 2 in the denominator gets cancels up. Integration m term is p into x, dou m by dou p term is into x dx divided by ei. Now what is the value of x now? X I have started from point B, I have considered from point B and terminated at point A. At any distance x, I shall mention it here. So limits of x will be, when it originated from point B, x value is 0. When it terminated at point A, upper limit of x will be L. So limits of x will be 0 to L. So integration will be 0 to L px square dx divided by ei. Throughout this particular variation of x, p will remain as it is. So you can take p common outside, 0 to L x square dx divided by ei. Integration of x square will be x cube by 3, 0 to L, and 1 by ei consider on towards the right hand side. Or else p divided by ei, substitute the limits here, L cube by 3 minus of 0, which will be pl cube divided by 3ei. This is what is the deflection at point B. That means this particular deflection value what we have calculated is pl cube divided by 3i. This same value we had evaluated by moment area method, conjugate beam method, strain energy method. In all those particular methods, the values remain same. So whichever method you are going to adopt, the value of the deflection will not change. For a particular type of beam being subjected to the similar type of loading, the value of the deflection will remain same. Only variation is the method that we are going to adopt. So deflection at the free end of the cantilever beam is pl cube by 3ei. Now next task is to find out. So deflection is been calculated as pl cube by 3ei. Next we need to find out the slope at that particular location. To find out the slope, I will redraw this particular beam again. Then this will be the elastic curve. Slope being considered at the free end as theta b. To find out this particular theta b, I shall again consider a section here at any distance x. Moment will be p into x. Moment shall be considered as p into x. Now here partial differentiation, earlier case it was partial differentiation with respect to load to find out deflection. To find out deflection, it was partial differentiation with respect to load. Now to find out slope, it was partial differentiation with respect to a moment. Now if I consider this equation as it is, I will yield this particular term as 0 because I don't have a moment. So that is the reason why I had entrusted before to impose a rotation force if we don't have, and that rotation force is called as a dummy moment. So introduce a dummy moment at a point where slope is introduced, dummy moment at the point where slope needs to be calculated. So here I will be introducing dummy force or dummy moment at point B. So this expression will be modified as P into X plus of M. For M we are not going to multiply any perpendicular distance, so equation has been kept as it is. Now if I partially differentiate this, first term P into X we don't have any expression of M, so it will come as 0. Second term will be 1. So dou m by dou m will come as 1. So same thing we need to substitute in the expression for the strain energy. So to find out slope, theta b will be equals to integration 2m dou m by dou m dx divided by 2ei. So earlier term it was dou m by dou p, now it is dou m by dou m. So 2 in the numerator and 2 in the denominator gets cancelled some. So integration 0 to, so section x will vary from b to a. So when it is at b, x value is 0, and when x is at a, x value will be L. So limits of integration will be 0 to L. M term is px plus m. Dou m by dou m term, what we have, the differentiation, partial differentiation term as 1 dx divided by ei. Expanding this particular bracket, px plus m dx divided by ei. In reality, m does not exist. You have introduced as a dummy moment. For that reason, put m is equal to 0 because it is a fictitious moment. Or else you have created as a moment. So put it as 0. So if you are substituting at 0, so this will be 0 to L px dx divided by ei and theta b on the left hand side. So integration of this will be p divided by ei outside, within the integration term 0 to L x dx, theta b term kept as it is. So theta b will be equals to p divided by ei, integration of x square will be x square by 2, 0 to L. P by ei, substitute the limits of integration, L square by 2 minus of 0 theta b. Reframing the equation, theta b will be equals to PL square divided by 2ei. This is what is the slope at the free end of the cantilever beam, which is PL square divided by 2ei. That is, slope is PL square divided by 2ei. PL square divided by 2ei is the slope at any point. That is at the free end of the cantilever beam, and deflection is PL cube divided by 3ei. This is how we are supposed to find out slope and deflection by Castiglione's theorem. So Castiglione's theorem is small review. If you partially differentiate strain energy with respect to load, we will be getting the deflection at that particular location. Likewise, if you partially differentiate the strain energy with respect to moment, we will be evaluating the slope at that particular location. And when we partially differentiate, we need to ensure that a concentrated load or a concentrated moment should be present at that particular location wherever deflection and slope needs to be calculated. If not, we need to introduce a dummy force and a dummy moment and later equate it to 0 during the process of integration. So further we shall solve with some more problems related to Castiglione's theorem. Thank you. Have a nice day.